This is problem 125 from chapter 12. The car travels around the circular track, shown here, having a radius of 300 meters, and remember that for a circle, the radius of curvature is equal to the radius, so this we can call rho is 300 meters, and that's the rho that we have in our formula here. Such that when it is at point A, it has a velocity of 5 meters per second. It's increasing, the velocity is increasing at a rate of 0.016 t, so that's v dot, where t is in seconds. Determine the magnitude of the velocity and the acceleration when it has traveled 1/3 of the way around the track. So we want the magnitude of the velocity and the acceleration at some time later. So I called that point B. It's traveled 1/3 of the way around the track, so this angle here would be 1/3 of 360. Okay, so remember that v dot, that's the tangential component of the acceleration, which we can see from this equation here. But v dot is also equal to dv dt. And so I can say that's equal to 0.06 t. And then I'm going to bring the dt over to the other side and then integrate. At point A, let's say that is time 0, and at point A the velocity is 5 meters per second. I want to know the velocity at some time later. I don't know what the time would be then. So let's just say this is v and this is t, and then that will give us an equation for the velocity as a function of time. So when I integrate on the left-hand side, I just get v, plugging in the limits of integration, that is v minus 5. On the right-hand side, I can pull out the 0.06. I integrate t with respect to t, I get 1/2 t squared. I plug in the limits of integration, let's just put the 1/2 in the denominator, and I get 1/2 t squared minus 0. So there you go. Then let's solve this for v. So this is going to be v as a function of t. I just have to add 5 to both sides, but I can say half of 0.06 is 0.03. Okay, so now I have an equation for the velocity as a function of time. Let's go back and just see what we're looking for. So the magnitude of the velocity at point B, well, I could find that if I knew what the time was at point B. And the magnitude of the acceleration at point B. So for acceleration, I need v dot, which I have, but I still have to know the time. I need v squared, so I need the speed at point B. I need the time at point B, and I know what rho is. Because we had the velocity as a function of time, we did this equation here. But in order to find the time at point B, I'm going to have to integrate again, because although I don't know what the velocity is at point B, I can figure out what the position is at point B, because I know this is supposed to be a circle here, although, well, part of a circle, although it doesn't look like it. So this radius, the distance from here to here, is going to be the 300 meters, which should be the same as the distance from there to there. So if s is equal to 0 at point A, at point B, s is equal to, it's traveled 1/3 of the way around the circle. The radius is 300 meters. So for a full circle, you would do the radius times 2 pi to get the circumference, but we want 1/3 of the circumference, or this is also using the arc length formula, where it's the radius times this angle here, which is 1/3 of 2 pi. And that is 628 meters. So that, I guess we should call this S sub B. Okay. So now I have the velocity as a function of time, but I know that the velocity is equal to ds dt. So I'm going to use this and this now to say, well, put in the velocity here, then bring the dt over to the other side. So we have ds is equal to 0.03 t squared plus 5 dt. Then we integrate from, we said this is s at point B. Maybe I should say if SA is equal to 0. So we're going from 0 to 628. And the time, the time at point A is 0. We said that there. And I'm looking for the time at point B. I'm going to put that in as my upper limit of integration. And remember that if you're not sure whether or not you should be putting in values for the upper limit of integration, you can always leave the upper limit symbolic and then plug in values later. So this is leaving it symbolic, which was a good idea because I wanted a function for the velocity. Velocity is a function of time, but here we can go ahead and plug in numbers. Okay, so then on the left-hand side, I just get 628 because it's just ds. And then on the right-hand side, I raise the power. The new power is 3, divide by the new power, so that's 0.01 t cubed plus this would be 5t. And then I put in my limits of integration, but the lower limit of integration is 0, so this would just be 0, and the upper limit of integration is tb, so I could just change that to a tb, and that is my equation. Well, that's how I'm going to find tb. This is tb to the first power. This is tb to the third power. So what I would do here is just use a computer to find it, to find tb. So using a solver like Wolfram Alpha, we find that tb is equal to 35.57. It's not going to give you the units, but the units should be seconds. Now, if you use a solver, you should get more than one solution, but the other solution is imaginary. Actually, there are two imaginary solutions. We don't want imaginary solutions for time. So we keep the real solution, and it should be positive, so that leaves us with the 35.57. I think from here on out, it's just plugging things in. So I might have you do that on your own. Let's just take a look at what we have. We need the magnitude of the velocity. So we still need to find that. Oh, but we have our equation here. So you just take the 35.57 and plug it in there, and you'll be good. That will give you the velocity at point B. Okay, then for the acceleration, you need v dot, so you plug in the time there. V squared, you're going to get that when you plug this time in here, and rho, which you have. Okay, so you can try and do it on your own, and then I'll show you what I get for that. Okay, so here we go. We need to know the velocity at point B, so I take this equation, I plug in the time at point B, I get 42.96. That is the velocity at point B. Okay, then for the acceleration, I have this vector here, and v dot I have an equation for, so I plug in the time at point B to get v dot at point B, and that's 2.13. So that's the tangential component. For the normal component, that's v squared over rho, so I plug in the velocity I have at point B, square it, divide by rho, I get 6.15. These are the two components for the acceleration, so I square them, add them together, take the square root, and I get 6.51, and that concludes problem 125.